Hello, everyone. I'm Judith Shank, and I'm a Senior Project Manager at Lytle Water Solutions in Highlands Ranch, Colorado. I'm a hydrogeologist, and my specialty is numerical groundwater modeling. Today, we're going to discuss multi-modal analysis for groundwater models and how that's a useful tool for assessing prediction uncertainty. Some points of discussion for this talk include reasons to consider multi-modal analysis, steps in performing a multi-modal analysis. I have an example problem to walk you through the process. And finally, some conclusions. The data we collect when developing groundwater models consists of geologic, geophysical, and hydrogeologic data. We read published reports, and we collect observation data by measuring groundwater levels in wells using either a measuring tape or data loggers. And we may conduct studies such as gain-loss studies along a stretch of stream to understand how much groundwater is moving into or out of a stream or of a surface water feature. Taken together, these data provide a window into the unknown groundwater flow system. We develop a conceptual model from our data, but we only have a general idea about the groundwater flow system. Our picture is not completely clear. In developing a model, we need to consider both what we know and also what we don't know. Considering what we don't know and testing alternative model hypotheses is important to assessing the uncertainties of model predictions. In not considering alternative models, we reject by omission other possible interpretations of the groundwater flow system. Multi-modal analysis provides decision makers with critical information regarding uncertainty of model predictions. So what is the modeling goal? For many models, we want to reproduce the system response that we see in our observation data. And if we can reproduce a groundwater system response, that's an indication that our model represents the groundwater flow system. However, because of our limited data, a different model construct may also produce a similar response and may provide a reasonable match to the observation data. So how do we know which model is more representative of the groundwater system? Well, multi-modal analysis accounts for uncertainty associated with model structure. Models are ranked, and a probability is calculated that a model and a set of models represents the true but unknown groundwater system. It provides a more realistic assessment of uncertainty of prediction. And multi-modal analysis removes the bias that exists when only a single model is considered. How different are the models in a set of models? Models can be variations of a single model in terms of model structure. Models can also be clearly distinct from each other. You can even have different models of an aquifer that can be constructed using different groundwater modeling software. The one caveat is that all models are calibrated with the same observation data set. This is because the model error is one of the components used to compare models. The model error, also referred to as the residual variance, is the error that remains after a model is calibrated. This error is only comparable if the same observation data set is used to calibrate each model in the set. Evaluation of model uncertainty using multi-modal analysis provides a joint probability, which is the likelihood of two events occurring together. The total uncertainty equals within model uncertainty and between model uncertainty. Within model uncertainty is the uncertainty of estimated model parameters for an individual model. Between model uncertainty is the uncertainty of model structure between models. When you add those together, you get the total uncertainty, which is the joint probability. I'm going to go through the steps for performing multi-model analysis, and I'm going to explain how the information criteria equations are used to rank models. And I have an example which uses a simple synthetic problem so that you can follow the process as I go through the example. We begin with a simple one-dimensional groundwater system. On the up gradient end of the system is a lake, and then on the down gradient end is a stream. And the distance between the lake and the stream is approximately 1,000 meters. The aquifer thickness is about 10 meters. and the difference in elevation between the lake and the stream is also about 10 meters. Note that there is a significant amount of vertical exaggeration in this figure. Well, what do we know about this system? We have collected groundwater level data, represented by the blue circles. We may also have measured or estimated the amount of flow into the groundwater system from the lake. What we want to know is, if we apply recharge to an area in the field, what will be the change in water level at the location of the yellow circle? What we don't know is, what are the hydraulic characteristics of this aquifer, and how should we represent that in our model? We begin by creating a set of models, and we calibrate each model in the set using a non-biased method such as nonlinear regression. After each model is calibrated, a stress can be simulated and predictions can be made. We're going to take this groundwater system and create our model. First, we begin by establishing our boundary conditions. We have a constant head in the up gradient end representing the elevation of the lake, and a constant head at the down gradient end representing the stream elevation. We have our observations of water levels, which are the blue dots, and we have a flow observation. Our simplest model is going to have two hydraulic conductivity parameters, so we're going to create two zones of hydraulic conductivity in the model. After the model is calibrated, we're going to simulate recharge in the model and the same location the recharge would occur in the field. And then we may want to look at what is the change in water level at the location of the yellow dot as a result of applying that recharge. We may not know a lot about the geology in this system, and as a result, we may be unsure as to how we should represent it. So we began with the simplest model with two values of hydraulic conductivity with two zones. And we're going to increase the complexity of the models until we have 10 zones of hydraulic conductivity. This type of problem is called a nested problem. Each of these models will be calibrated, and then we'll simulate adding recharge to each one of these models, and then we will observe the change in water level at the location of the yellow circle. In this next step, we use an information criteria equation to calculate a model score for each model. Information criteria equations measure the strength of evidence that a model represents the true but unknown system. These equations are designed to find the balance between model fit and model complexity. Different information criteria equations use different measures to measure the strength of evidence. The example we use the Kashyap information criterion and also the Akaiki corrected information criterion, so you can see the different results you get depending on which criterion you use. All information criteria equations have the same general form. Every equation includes a goodness of fit term, plus there are penalties. The goodness of fit term refers to how well the model fits the observation data. The penalties refer to how complex the model is, and depending on the information criterion you're using, these penalties vary. The idea is, as the model becomes more complex, you should see a better fit of the data, so your goodness of fit value should go down. When these two are added together, you get an information criterion score, and the model with the lowest score and a set of models is assigned the highest probability that that model represents the true but unknown system. This is the equation for the Kashyap information criteria. Don't worry about the math, but I do want you to see the different terms that I was discussing. This first term is the goodness of fit term, and this term is common to all information criteria equations. KIC has another term, which is a penalty for the number of parameters in the model. In addition, KIC has a term for expected Fisher information, which is related to the model complexity. Fisher information is a quantifiable measure of how much information the simulated observations in the model are providing about the estimated parameters given the observation data set and the model structure. Fisher information generally increases with increasing model complexity if the model is well-founded and there are not high correlations between model parameters or insensitivity of all simulated observations in the model to one or more parameters. This graph shows the components of KIC. In red, you can see the goodness of fit term, and in blue, you can see the sum of the penalties assigned because of model complexity. The simplest model has the largest goodness of fit term, but it has low penalties because it is only 2 parameters. As we get up to the most complex model, you can see the goodness of fit has improved with our model complexity, but our penalties have also increased as a result of the increasing complexity. Next, we calculate the IC score, and we rank each model according to its score. These are the scores we get when we sum together the goodness of fit term with the penalties for model complexity. And interestingly enough, the simplest model and the most complex model have the lowest KIC scores. And here, you can see how these all rank according to their scores. Once the models are ranked according to the information criterion score, each model's probability can be calculated. Once the models are ranked, the model probability is calculated using an exponential weighting function. The weighting is based on how far each model is from the model with the lowest IC score. This is called the Kullback-Leibler distance. These are the KIC model probabilities calculated based on their scores. You can see the simplest model with 2 parameters has a probability of 50%, and the most complex model with 10 parameters has a probability of 41%. The other 3 models have low probabilities. This probability is the probability that the model represents the true but unknown groundwater flow system. Now we can calculate the model average prediction and uncertainty on the prediction based on each model's probability. This shows the probability density function of the prediction for the 2K and the 10K models. The true prediction is the open black circle. You can see that the 2K model has a broader range of uncertainty because the curve is broader and has a lower peak than the 10K model. The 10K model probability density function is narrower with a higher peak, and the estimate of the prediction, as you can see by the arrow, is close to the true prediction. This is not always the case, because for this example, which is a synthetic problem, we have good data with no noise. Field observation data include varying levels of error in the data, and although you can get a better fit with a more complex model, that does not always translate to a more accurate prediction. Now we're going to calculate the model average prediction and the uncertainty on the prediction based on each model's probability and the model set. This is the model average probability density function in white blue. I include this probability density function for the 2K and the 10K models because these 2 models are the most influential in developing this model average probability density function. And you can see how the peak is not as high as the 10K model, but higher than the 2K model, so it falls between these 2. And also, the width of the curve is between the 2K model and the 10K model. This is the model average prediction. And now you can see the model average probability density function. What we hope to do when we consider multiple models of a system is to capture the true prediction, which we never know, within a reasonable range of results. You might be asking, why is it that the 2K model has such a high probability when the 10K model produced a better model fit? If we look at the distribution of model observations, you can see that there is a general change in the groundwater flow gradient. The upper portion has a gentler gradient, and the down gradient portion is a bit steeper. The 2K model was actually able to capture this, so the 2K model had a correct structure, and therefore it explained a lot of the data. Plus it was not very complex, so it didn't have a lot of high penalties because of the complexity of the model. I want to speak a little bit about using different information criteria equations. So here we're going to look at the Akaiki corrected information criteria. And again, you don't have to worry about the different math in here, just the different components of the equation. It has the same goodness of fit term as KIC, and it has two penalties. One is for the number of estimated parameters, and then it has a second order bias correction term. So let's look at what happens with the penalties as the models become more complex. If we compare the KIC penalties to the AICC penalties, you can see that as the models become more complex, the AICC penalties increase at a greater rate than the KIC penalties. And now if we look at the model probabilities, and I want to point out that AICC refers to model weights instead of probabilities, but to be consistent, I'm going to refer to probabilities for both KIC and AICC. You can see that AICC favors the simplest model, with an 81% probability that that model represents the true but unknown system. However, because of the penalties imposed by AICC for this particular problem, you can see for the most complex model, there's an extremely low probability that that model represents the true but unknown system using AICC. So you can get very different results, and it also depends on your particular problem and your particular set of models that you're using. Here is another example with results presented in a slightly different way. In this example, both recharge and hydraulic conductivity are estimated. And we have increasing model complexity from left to right. However, you can see that some of them have the same number of parameters. The second model with 6 parameters has 2 zones of hydraulic conductivity and 4 zones of recharge, whereas the third model has 4 zones of hydraulic conductivity and 2 zones of recharge. So although they have the same number of parameters, they have different model structures. The open circles are the true prediction taken from a synthetic model again, and the black diamonds are the predictions made by each one of the models. The dashed lines are the 95% confidence interval on each of the predictions. You can see, for example, the second model, which has 2 zones of hydraulic conductivity and 4 zones of recharge, has a larger uncertainty. The fourth model with 8 parameters with 2 zones of hydraulic conductivity and 6 zones of recharge. Also, looking at this, you can see that the second model prediction falls closest to the true prediction. This is the KIC model probability calculated for this set of models. Here, the simplest model with 2 zones of hydraulic conductivity and 2 zones of recharge has a probability of 63%. And the third model with 4 zones of hydraulic conductivity and 2 zones of recharge has a probability of 37%. Finally, we look at the KIC model average result. The blue dots represent the KIC model averaged prediction of change in head, and the dashed line represents the model average 95% confidence interval on that prediction. And you can see that this confidence interval is between the confidence interval of the first model and the third model. But I also want to point out to you that the prediction of the change in head was not the closest to the true prediction. However, what's important here is that we did capture the true prediction within the 95% confidence interval. And this is important because we'll never know what that true prediction is. I know I said that previously, but we want to try to capture it within some reasonable range. So what have we learned? Our understanding of the groundwater system is limited, and more than one model may explain the observation data that we have. Multi-modal analysis is used to evaluate multiple models of the system. Information criteria equations used to rank models and assign model probabilities are designed to find the balance between model fit and model complexity. Different information criteria equations, however, can produce different results. And multi-modal analysis provides a more realistic assessment of prediction uncertainty because different model structures have been considered. Multi-modal analysis has practical applications. We are currently collaborating with another group on a project with multiple models of the same groundwater system. We are able to evaluate each model, make predictions, and inform decision makers with information they need by providing them with a realistic assessment of prediction uncertainty. Thank you for your interest. And if you have any questions, you can reach us at Lytle Water Solutions.